Okay, yay. It is now time to learn about conservation of momentum. We're going to do lots of problems. That's what today is all about, just doing problems. Conservation of momentum. One of the most important conservation equation thingy that you'll ever have. Conservation of momentum. Here we go. Momentum. Having some trouble with the spelling here. Okay. If a system is isolated, and if a system is isolated, then the initial momentum is going to equal the final momentum. That is, you're going to have momentum being conserved. Your momentum will not change. Things can happen to your system and it doesn't matter. Momentum will remain unchanged. So let me ask you this. What does it mean for a system to be isolated?
Wait. I think something zero.
So someone raise their hand so I can call on you? What does it mean? Yeah, Sean.
External forces equal to,
Yeah, if the sum of the external forces is zero. You can have external forces, they just have to all cancel, right? So if the system is isolated, that is the sum of the external forces equals zero, then we get to say that momentum is going to be conserved, alrighty? And we're going to find for most situations that that we're dealing with momentum, that's going to be an isolated system. Here, let me give you a quick example. Okay, here comes example number one. And I'll do this example. Imagine I'm on wet ice, or rather we have wet ice so that the friction force is equal to zero, alrighty? And I've got two people on this wet ice. I've got a 100 kilogram man and I've got a 50 kilogram little girl, okay? If I consider the man and the little girl as my isolated system, as my system rather, are they isolated? Well, there's lots of external forces. There's gravity and normal force, but what do you notice about the gravity and normal force?
They cancel.
They cancel, they're equal and opposite. So yeah, this is an isolated system. And so this guy and this girl are going to push against each other. And a moment later, this girl is going to be going off at 5 meters per second, and the guy is going to be going off at some unknown speed. Well, many of you could probably just look at this and tell me what the speed is. How many people here say he's going to be going off at 10 meters per second? Good, I only faked out a couple of you. How many people say he's going to be going off at 2.5 meters per second? Oh, many more of you. Okay, well, let's go ahead and do the problem. When you have a isolated system, step one is usually to draw a picture, because a picture makes things really obvious to you. But step two is always going to be initial momentum equals final momentum. You'll find that that really orders your thinking. Initial momentum equals final momentum. You don't get caught up juggling numbers and trying to do it in your head. Just write down initial momentum equals final momentum. Tell me, initially, what's their momentum? They're at rest, about to push against each other. What's their momentum initially? You guys getting zero?
Yes.
Yeah, so I got zero momentum, okay? Then a moment later, they've pushed against each other. You've got the 50 kilogram girl, the 50 kilogram girl going off at 5 meters per second. You've got the 100 kilogram guy going off at some unknown speed, which I'll call V. Then we solve for V, and I end up with V equaling negative 2.5 meters per second. Now, you tell me, why is his V negative? What does that mean? What does that mean for this guy? Yes, Alexis?
going the opposite direction of the
Thank you. He's going the opposite direction of the girl. Good job. Yeah, if we're going to define this direction, if we're going to define the right as positive, then this dude ended up going to the left. You see? His velocity is 2.5 meters per second to the left. Because remember, momentum is a vector, velocity is a vector, force is a vector, and so you get positive and negative versions of it. You guys ready to do a problem like this on your own?
Yes.
Okay, here we go. I'm going to, let's see which one I'm going to do. I might change what I do. Oh, let's do the rocket ship and the fuel. Yeah, let's do that. Okay. Number 2, example number 2. Okay, a 250.50 kilogram rocket ship is going 52 meters per second east. Okay? It expels fuel It expels fuel and now is going, I'm going to change this from last period, 49 meters per second. Oh wait, I'm so sorry. It expels 0.50 kilograms of the fuel and now is going 49 meters per second east. Find the velocity, both speed and direction of the fuel. Okay, please write this down. What should I do first? Yeah, I would probably, something this complicated, I would probably draw a picture. You know, there's an initial and a final situation. The initial situation is the rocket ship going 52. The final situation is an expelled fuel, you know, and it's going 49. Okay, so let's go for it. First of all, here's my rocket ship. We'll put a little star on it because this is an American rocket ship. Alrighty, and it's going 52 meters per second. It is a 250.50 kilogram rocket ship. And then it expels some fuel, blast. And now my rocket ship is going 49 meters per second. This is a 250 kilogram rocket ship now. Why'd the mass of my rocket ship change from 250.5 to 250?
You lost fuel.
Yeah, I just expelled a half kilogram of fuel. Tell me, in which direction did I expel the fuel? You thinking to the left? Because that's where fuel goes, it comes out the back. If that's what you think, that's fine. 0.50 kilograms. And the velocity is unknown. Okay? By the way, does anyone disagree? Does anyone think the fuel got expelled to the right? Oh, let's find out. Next step, initial momentum equals final momentum. And now let's write this down. You tell me, what should I put for the initial momentum? What's that? Who's saying that? Monty, is that you? Say it again, Monty. No, it's not zero. This guy's got momentum initially. This is my system. My system is the rocket plus the fuel. When the fuel gets expelled, that's still my system, rocket plus fuel. So tell me, what's the momentum of my system initially? Yes, Logan? Yeah, let's do that. So my initial momentum is 250.5 times 52. Now, my final momentum, I've got 250 times 49, 250 kilograms times 49 meters per second plus the fuel times its velocity, right? 0.5 v. Now I'm going to solve for v. $250.5 times 52 minus 250 times 49 divided by 0.5, 1550 approximately. Please notice, did you guys get positive 1550 when you did your calculation? So tell me, what direction was that fuel expelled?
Right.
To the right, which, Logan, you had it right all along. Yeah, you guys okay? That rocket fuel didn't get expelled to the left. No way. It got expelled to the right. Correct? My rocket fuel got expelled to the right. How did I know it got expelled to the right? What did the rocket ship do? Slow down. If you're going to slow down, you better expel that fuel to the right if you're going to slow down. You see? So yeah, the answer is 1550 to the right. (1550 meters per second east). You see? So again, this is a situation. By the way, the only way you're going to make rocket fuel go that fast is if you burn it. Okay. Let's have you guys do another one. Here's one that you guys are going to do on your own. Initial momentum equals final momentum. I have a fish. Okay, he is a 4-kilogram fish, and he's going to the right at 5 meters per second. I have here a fish. He is a 1-kilogram fish, and he is at rest. My system is going to be the two fishes. What do you suppose happens next?
Chomp.
Yes. Chomp. And so now, I've got I've got my big fish, and I got my little fish. Okay? And I want to know what speed he's going to the right. Please do this problem. How fast is that big fish going to the right? I will walk around and help you. I gotta give you a minute.
That momentum plus that momentum.
Okay, so initial momentum is correct, yeah. That's what it is. Is that your final answer? You are correct, sir. Alrighty, what's the correct answer here?
Okay.
Alright, write down the stuff. Yay, you're correct.
Big
Yes, I see the correct answer in your future. Good for you, Brianna. Good for you. You're gonna get it right. Yay. Yay.
I accidentally wrote down for small fish.
Okay. How many kilograms does the big fish and the little fish together weigh? No, your left side is correct. He's a 4 kilogram fish. Okay, yeah. But we have 5 times 0, but it's not, I mean, he's going in a direction. He's going to the right. You just got to figure out how fast he's going. But now he's no longer a 4 kilogram fish. Yeah. Good. Good. Okay. Pooja? 4 times 5 equals 20, not 9. Glad I could help. You gotta get more sleep.
No, because I'm trying to get down the quietly, but
Yay. Yay. Is it 4?
yeah. My mom's like, yeah.
All right. Hey, looking good. Okay. Okay, let's take a look at this. And I really urge you, step 1 should always be initial momentum equals final momentum. After that, you can plug it in and you'll get right answers. So my initial momentum, I've got a 4 kilogram fish going 5 meters per second. The little fish makes no contribution to the momentum of the system. Look who's here, if it isn't Ice. All righty. With a forged pass. Good for you.
Yeah. Most definitely.
Now, who is this?
Romero.
Romero?
Counselor.
Nick Romero?
Yes, the one and only.
Okay. So your final momentum, this is now, he is no longer a 4 kilogram fish, he is now a 5 kilogram fish. Like me, after I go to a all-you-can-eat buffet, I am no longer a 260 pound fish. But anyway, so we got times V, and then you get V equals 4 meters per second. And pretty much everyone got it right. You guys okay with that? Okay, then hey, I gotta tell you something about high school physics, okay? We, in high school physics land, we're gonna assume that momentum is conserved in all collisions. That's what we're gonna do. Assume momentum is conserved in all collisions. I mean, essentially, in high school land, we're going to say that all collisions happen under circumstances of an isolated system. Now, that makes sense for the most part. You know, these 2 fish, they're isolated because there's gravity down but buoyant force up, so there's no net external force. And when you have 2 ice skaters, which we're about to see, colliding, we're going to say they're, what do you call it? They're isolated because normal force is equal to weight. Or look at here. Tell me, these balls, why am I going to say that these 7 balls are an isolated system? Gravity's acting down on them. Yeah, but tension's acting up, and so they're isolated. So we'll be able to look at these balls and see what happens. Okay, so I just want you to know that in physics land, high school physics land, we're going to say that momentum's conserved in all collisions. Even if, theoretically, even if 2 balls hit each other in the air so that you're going, wait, there's a net force of gravity. Even when that happens, we kind of say, okay, yeah, but you know, during the short time that they're actually interacting with each other, gravity doesn't really do that much of an impulse on them. So we're going to say that this is isolated anyway, even though it's not. I don't know, whatever. You know, I'm saying this stuff on video and it's all lies. Just believe me. So anyway, here comes our next one. We're going to keep doing examples till you can't do any more. I now have 2 ice skaters. I've got a 100 kilogram ice skater, and he's going 2 meters per second. and he's got his girlfriend coming at him. She is a 50-kilogram ice skater, and she's going 5 meters per second. Right? 100 kilograms going 2 meters per second. 50 kilograms going 5 meters per second. And then they hug. And it's beautiful. And then they drift off together, her in his arms. Is that okay? And so I need to know, get speed and direction. What's their speed and direction after the collision? After she's jumped in his arms. What are you guys looking at? There's a bird in my window. If that bird comes into this classroom, I'm going to be very put out.
He's trying to learn
Put out.
Have you ever had a bird in a classroom?
Yes.
Oh my God.
Do you know how many people freak out for no reason? It's Hamarangi.
Go find my speed.
Okay, please do this now. Good luck.
You're not gonna drop Wanji, right? I feel like it's gonna drop me.
Hey.
Yeah, but we're on ice. It's gonna hurt.
Oh, there's another wire.
What?
Ah, stupid thing. Ah, stop it.
I've been
Did I draw my thing clearly enough that he's going 2 meters per second to the right and she's going 5 meters per second to the left?
Yeah.
Okay, I'm gonna walk around and help you. What'd you get? I'm so sorry, that's wrong. Wait, before you do anything, tell me, the woman who's moving 5 meters per second to the left.
Oh,
Tell me
yeah.
about her movement.
That's
What?
Chris, you're good.
Chris is down. We literally just fucking idiot. Shut up.
Yeah, she was going a little slower, they would slam into each other and be at rest. Yeah, that's the right answer.
Because you have to get the So his momentum is the 100.
I accidentally did.
And then hers
What's the direction?
What'd you get? Yeah, that's correct. That ends up being correct.
I have to get my
You're
coffee.
correct. Come on, don't forget the girl, she's going 5 to 7.
Because you have
No, I'm taking it to sale.
Hey, listen, buddy. No, buddy. No, yeah, there you go.
All right, good. Great.
I don't want to get in trouble.
That includes me.
What?
Hey, the girl.
Yes,
Well,
Mom.
first of all, wait. That should be a plus in there.
said girl.
Initially,
How do I even get my
see what's happening on the left of the
You gotta find one name.
Everything happens on the left.
You gotta find one name.
Is your initial condition. So the momentum of the girl is going to be 100 times 2 and then 50 times 5.
Did you just slip that in?
That's one more thing I need you to notice. You notice her 5 is to the left. So you're not going to put positive 5, but you're going to put Yeah, and then that's going to equal, and then after they hug, what is their mass together after they hug? Yeah. Okay. Alrighty, coolio. Okay, what the heck? So you can't, oh, okay. I thought maybe you're one of these people who can't live life in real life. You have to live it like through, camera.
You have to have something like this.
Okay.
It's like looking at you.
Initial momentum is Your initial
I feel like I'm not considered it strong when I go
momentum is their momentum before the collision. So that's the big guy. Right, the initial momentum, if I can show you, Tiffany, your initial momentum is all of this. After the hug, that's your final momentum. Yeah.
I look bad. I'm not gonna lie. I told my mom that she checked me
Okay, guys. Okay.
I just stared at it.
There's something that this class is having difficulty with that other classes haven't so much. So I need to make it really, really clear. There's an initial situation and a final situation. And your initial situation is always going to be all of the momentum before the collision. And your final situation is what your momentum is after the collision or after the interaction. Because I have a lot of people saying that the initial momentum is just the dude, but no, the system consists of the dude plus the girl. My system is the dude plus the girl, so the initial momentum of the system has to be the momentum of the dude plus the momentum of the girl, right?
Yeah.
That's the total momentum of the system before the collision. So when I do initial momentum equals final momentum, okay, my initial momentum is the dude plus the girl, right? That's my total initial momentum, except for one thing. The girl is traveling to the left.
Yeah.
So what kind of momentum does she have?
Negative.
Yeah, negative, or her velocity is negative. Then after they collide, now they are one big 150 kilogram mass of humanity moving in one direction together, right? Times v, and so I end up with negative 1/3 meters per second equals v. Okay, which means, which direction are the two of them moving after the collision?
To the left.
Yeah, now is there some way I could have looked at this initial situation and been able to predict that after they collide they're going to move to the left instead of the right?
Her velocity is higher.
Wait, what's that, Izina?
The girl is moving faster than the guy.
No, it's not because she's moving faster, that's not it.
Oh, that's the same thing I said.
Go ahead.
Her momentum's greater.
Yeah, her momentum's greater, right? If she's a 20 kilogram girl, the fact that she's moving 5 meters per second isn't going to make them move to the right or move to the left. The issue is the momentum, not just her speed, you know? So yeah, so that's it. So moving 1/3 meters per second to the left. Okay, let me just demonstrate this a little on my demo table, and then I got to tell you about the two types of collisions. Here. Okay, let me get this off.
Android.
Alrighty. Remember the first problem we had where the 100 kilogram guy pushes off the 50 kilogram guy, and the 50 kilogram guy goes off at 5 meters per second, and the 100 goes off at 2.5?
Yeah.
Okay, so this is just a quick demo of that, right? I'm gonna release the spring, and what should be the ratio of their two speeds after I release the spring? Oh, by the way, this is 1,000 grams, and this is 500 grams. So what should be the ratio of their speeds after I release the springs? Yeah, 2 to 1, here we go. Does that guy look like it's going twice as fast as that guy?
Yeah.
Pretty much, I don't know. Close enough. Okay. You guys okay with that? Or here, let me give you another one. How about when the girl, how about the fish? Here I got a 5 kilogram fish, about to eat a 4 kilogram fish eating a 1 kilogram fish. Okay? So, here, just 1 second. I'm going to do this sort of thing. Okay, so watch. Woo-hoo. You guys okay with that? That's, he's not really sticking, is he? Maybe he needs some duct tape too. Here, we're gonna get some duct tape on there. When in doubt. Okay, here we go. You guys okay with that? Let me ask you this. What if the 1 kilogram fish were to eat the 5 kilogram fish or 4 kilogram fish? What would happen? What would the relationship between the final velocity and the initial velocity be? Like if this guy went like this and hit that guy, how fast would that guy go off? How many people think not that fast? Yeah, here. Yeah, not that fast. Whoops. Yeah, because even though he's going really fast, even though he's going relatively fast, how much momentum does he have? Not much. Why doesn't this guy have much momentum?
Because he's so little.
Yeah, very little mass. So I have to really have to go fast to make that guy go a little bit. You see what I mean? Okay, and then finally, we've got these two isolators. Whoa. The 50 and the 100. Okay. Tell me, what if I make it so that this guy's speed is exactly 1/2 this guy's speed, and I have them collide with each other? What's going to happen next?
Bounce.
What's that?
Bounce.
Okay, well, I've got the tape there so they won't bounce. So let's say they don't bounce. Let's say this guy's going 1/2 the speed as this guy. So tell me, what would be true about their momentums? If this guy has 1/2 the speed of this guy, what's true about their momentums? Yeah, they'd be equal and opposite. So when they slam into each other, what should be their final speed? 0, because what's their initial momentum? Right? If he's got 1/2 the speed and he's got twice the speed, do you guys see that the initial momentum of the system is 0? So after the collision, the final momentum has to be 0. So here we go, watch this. Oh, it'll be amazing. Oh, wait. So what did I do? Who did I throw too hard?
The heavy one.
Yeah, the heavy one I threw a little bit too hard, so here, let's try that again. I won't do the heavy one so hard. Wait. Okay.
Hey, there
You guys okay with that? Okay, so that's what happens. So if you were to like be skating towards your lover and the two of you, embraced, whatever the ratio of your masses are, the ratios of your velocities are going to have to be what? Like if the ratio of my mass to my lover's mass was 2 to 1, would have to be the ratio of our velocities?
1 to 2.
Yeah, 1 to 2, the inverse ratio, and then we could slam into each other and embrace and at least not be in motion. You know? Okay, great. Let me talk about something else now. 2 types of collisions. Okay. There are 2 types of collisions. And I'll tell you right now, elastic and inelastic. The first type is elastic. With an elastic collision, or another name for it is perfectly elastic, no kinetic energy is lost due to the collision. No kinetic energy is lost due to the collision. That means your kinetic energy is conserved. Whatever kinetic energy you started with, that's what you end with. Let me give you an example of a perfectly elastic collision. I have here a racquetball. It is a magical racquetball. It makes nothing but perfectly elastic collisions. So I'm gonna drop this racquetball, and the racquetball is gonna hit the floor and make a perfectly elastic collision with the floor. Are you guys ready for that? Perfectly elastic. Tell me, if I hold the ball from here and it makes a perfectly elastic collision with the floor, which means it doesn't lose any kinetic energy before and after its collision with the floor, how far up would you expect this ball to go?
Back to your hand.
Right to my hand, correct? It'd be perfectly elastic. No energy loss when it collides with the floor. Well, that's what's going to happen. Here it goes. This ball, I'm going to drop it, and it's going to come to this height because it's a magic, perfectly elastic ball. You ready? 1, 2, 3. Okay, well,
There we go.
it was close. Here, maybe I did it wrong. Here, maybe I was thinking the wrong thing. Here we go. Okay, now it's going to happen.
Getting closer.
Okay, so do we agree that this is not making a perfectly elastic collision with the floor? There's a name for that type of collision. It's called inelastic. So an inelastic collision, means kinetic energy is lost in the collision. Okay? For example, look at this situation with the two ice skaters. Was that a perfectly elastic collision? Did they have the same kinetic energy after the collision as before? Well, let's find out. Okay? The initial kinetic energy is going to be 1/2 times 100 times 2 squared plus 1/2 times 50 times 5 squared, right? Actually, it's -5 squared, but the square makes the negative go away. So initially, before they collided, they had 825 joules of kinetic energy. 200 for the guy and 625 for the girl. After the collision, they're now a big 150 kilogram blob going at 1/3 of a meter per second, right? That's 75 over 8. That's approximately, 9-ish, right? Or 7, wait. 75 over 8, 8 times 9, right? No, 75 over 9. So 9 times 8 is 72, right?
Yeah.
And that's 75. So that's about 9. Am I messing it up? That's 8. It's 8. It's 8. Whatever.
Close enough.
So tell me, was that a perfectly elastic collision?
No.
Not even close. They lost virtually all of their energy. This was akin to what I did here, where the two guys had kinetic energy. They slammed into each other, and then they were at rest. They lost all their kinetic energy. Tell me, where did all that kinetic energy go?
Surrounding.
What's that?
Surrounding.
Good, eventually to the surroundings, but let's talk immediate. Imagine what it would feel like if Brianna was to come at me at 12 miles an hour and I was coming at her at about 5 miles an hour. How would it feel?
Painful.
Yeah, it'd be painful, because what would Brianna be doing to my body? Exerting a force over a distance, right? She'd be deforming me, you see? She would just slam into me, See, and what do we call that when a force over a distance? Work. She'd be doing work on me, and I would be doing work on her. You see what I mean? We'd be deforming each other. Now, the thing is, if you do work on someone, if I come back to the way I was before, all my molecules are now moving a little bit faster. When you do work on something, you move the molecules faster. Has anyone in the class, and it doesn't seem to be popular among students nowadays, but has anyone in this class ever taken a paper clip and wanted to break it? So they go boop, 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 and then they break it? Okay, so you guys have, and have you ever felt the paper clip afterwards? The temperature of the paper clip? And what's the temperature like?
Warm.
Yeah, it's warm because you're doing work on the paperclip, and that work eventually becomes heat, and that's what happens. So when I asked where did the kinetic energy go, and you said heat, yeah, eventually that's very true. When you do work on somebody, eventually that work devolves into heat. Yeah, but I still want you to know that that kinetic energy went somewhere, and initially it went to work. It went to the work of deforming the object. That's why this guy hits the ground and it gets deformed when it hits the ground, then it unforms, and the fact is you lose some kinetic energy in this process of deformation because you're doing work on this ball and thus raising the temperature of the ball. So I want you to see something. First of all, inelastic collision, virtually all collisions in real life are inelastic. In real life, all collisions are inelastic. I mean, I can give you a collision that's almost elastic. Here, first of all, I can give a collision that's almost elastic, where essentially they're colliding via a spring, okay, where it goes like that sort of thing. That's kind of elastic, okay. Or I can go with these balls here, like if I lift one ball out, how many balls are going to come out on this side?
One.
Yeah, one, because this is kind of an elastic, a perfectly elastic collision. Okay, but not entirely. In real life, the only thing that has elastic collisions, you learn about them in chemistry.
Gases.
Yeah, ideal gas molecules. That's right, that's it. That's pretty much it. Because if ideal gas molecules didn't collide perfectly elastically, then they'd lose energy with each collision. Pretty soon all the gas molecules would lose all their energy and they'd all be on the floor, Let me ask you one last question. You'll notice when one ball comes out, one ball comes out there. And that's because momentum has to be conserved. This ball has a mass m, it hits with a velocity v. This guy with a mass m comes off at a velocity v. But momentum would also be conserved if this one ball hit and then two balls came out at half the speed. Why doesn't that happen, assuming that this is almost perfectly elastic? Why don't I get two balls with half a v coming off when one ball with a speed v hits? What would be wrong with that? Assuming that these collisions are, almost perfectly elastic. Momentum would be conserved. But what would be the problem with a single ball with a mass m hitting and two balls with a speed of 1/2 v coming off? Yes?
They'd have a different kinetic.
Yeah, sure, they'd have different kinetic energy, right? The single ball has a kinetic energy of 1/2 mv squared, and the double ball would have a mass of 2m, but a velocity of 1/2 v. Do you see that this ends up being 1/4 mv squared? And that's not what's happening. I'm not losing half of my kinetic energy with this collision. So yeah, it has to be a single ball comes out. By the way, you guys have seen this where two balls comes out? And you see it with three balls and three balls come out, you're okay with that? And if I have four balls, what's gonna come out? Four balls. You guys okay with that? Or five balls, five balls. And of course, as you know, six balls. And then finally, what happens with seven balls?
All of them go.
Yeah, nothing, it's just kind of swings. So you've got the other thing like this, where two balls and one ball, and then
Whoa!
two balls.
Wait a minute.
You guys okay with that?
Never failed to.
That's crazy.
Yeah, I like that. That's always my favorite. Alrighty. Well, hey, that's conservation of momentum. You get to do lots of problems tonight, and every problem I really urge you to write down initial momentum equals final momentum, and make sure you know what your initial momentum is. It's everything, the whole system. Good luck.